All right, class, welcome to our deep dive. Today, we're going to be looking at radiomics, where AI steps into the world of medical imaging.
Yeah, fascinating area.
You've all been working hard studying the lecture notes and research articles.
Yeah.
So let's unpack those and see what we can uncover together about how AI can analyze these medical images for diagnosis and treatment.
It really is remarkable how AI is being used to unlock that hidden information within medical images, things that might even escape the human eye.
Okay, so let's break this whole process down. What's the first step in this AI-powered medical investigation?
Well, it all starts, like any good investigation, with evidence. And in radiomics, that evidence comes from a variety of radiological images,
Right.
whether that's X-rays, CT scans, MRIs.
Okay, so we have our images. What's the next move?
Then we zero in on the specific areas within those images that need our attention.
Gotcha.
So think of it like a detective zeroing in on a crucial piece of evidence at a crime scene. We call these regions of interest,
Okay.
or ROIs for short.
So we've got our images, we've highlighted the key areas. Now, how does AI come into play?
This is where things get really interesting. We use algorithms to extract features from these ROIs.
Okay.
And these features are like measurable characteristics that describe the content of the image.
Okay.
Things like intensity, texture, and importantly, shape. It's as if we're giving our AI detective a magnifying glass and a toolkit to analyze every detail.
So it's not just about what we see, like on the surface of the image.
Right.
It's also those hidden details and patterns within it.
Precisely. And these features are ultimately what our AI models use to learn and make predictions.
So give us some examples of these features. What kind of information are we talking about?
Let's start with shape features, which are particularly important in medical imaging. Think about a doctor examining a tumor. They'll consider its size, its borders, whether it has a smooth or irregular outline. These are all aspects of shape.
Right.
That can provide clues about the nature of that tumor.
So it's not just about the color or the texture of the tumor on the scan. It's also about its shape and how it's growing.
Exactly. Shape can tell us a lot. And radiomics allows us to quantify those shape characteristics using specific mathematical formulas.
Okay, can you give us some specific examples of these shape features and how they're measured?
Sure. Let's just start with a simple 2D shape, like a circle.
Okay.
One basic feature is area, which simply means the total space the shape occupies. Then you have the perimeter, which is the length of its boundary.
All right, those are pretty straightforward. What about some of the more complex 2D shape features?
Well, there's compactness, which tells us how efficiently a shape fills its space.
Okay.
So a circle is very compact,
Right.
while a starburst shape with lots of outward points is less so.
So a low compactness in a tumor could be a warning sign,
Yeah, potentially.
suggesting irregular growth.
That's the idea. Then we have eccentricity, which measures how elongated a shape is. A stretched out oval has a high eccentricity, while a perfect circle has 0. So, doctors might use eccentricity to assess a tumor's growth pattern. A higher value there could indicate a more aggressive form.
It's fascinating how we can glean so much information from just a simple shape. What about when we move into the 3D world of medical scans?
That's where it gets even more exciting. Instead of flat pixels, we have voxels, which are like 3D building blocks. And we can calculate 3D shape features, which give us a much richer understanding of the object's structure.
So instead of just looking at a tumor's outline, we can analyze its entire 3D form.
Exactly. For instance, we can measure its volume, how much space it occupies in 3 dimensions. We can look at its surface area, the total area of its outer surface. And just like in 2D, we can analyze its compactness and how spherical it is.
So even though 3D adds complexity, the core principles of shape analysis remain the same.
Yeah.
We're trying to quantify the geometric properties of the object just in a more detailed way. But how do we actually visualize and analyze these complex 3D shapes? The lecture notes mention something called the marching cubes algorithm, which sounds pretty futuristic.
It does, doesn't it? It's actually a clever method for building a 3D mesh representation of a surface from volumetric data, essentially creating a digital sculpture of the object.
So we're transforming a series of 2D images into a complete 3D model of the object.
Precisely. And once we have this 3D model, or mesh, we can analyze its shape in a much more sophisticated way, which can be incredibly valuable for medical diagnosis.
Okay, I think I'm starting to grasp this. So we're going from images to regions of interest, extracting all these different features, including these fascinating shape features. But we're still missing a key player here, the AI. How do we utilize AI to make sense of all of this data?
That's where the real magic happens, but I think it's time to give everyone a moment to process this first part.
Yeah, I think that's a good plan. We've covered a lot of ground already, and I'm really excited to see how AI fits into all of this.
All right, let's get back to those AI-powered detectives.
Okay, I'm ready. So we've laid the groundwork. We understand how to extract all these fascinating features from medical images, especially those that reveal shape characteristics.
Yeah.
Now, how does AI actually put all of this information to work?
Well, imagine we've gathered all the clues. So you have your fingerprints, your DNA evidence, witness testimonies. Now we need that brilliant detective to analyze it all, make sense of the patterns, right? That's where AI steps in.
So the AI is like our master detective in this world of radiomics.
Precisely. We use machine learning, a subset of AI, to create models that learn from these features and then make predictions about a patient's condition.
So what kind of predictions can these AI models make in the context of radiomics?
Well, the possibilities are vast. We can train these models to predict the likelihood of a tumor being malignant or the stage of a disease. We could even predict a patient's potential response to a specific treatment.
Oh, wow. So we could potentially even use AI to personalize treatment plans based on the unique features extracted from a patient's medical images.
That's the ultimate goal. And the research and clinical trials in this area are showing some very promising results.
This is incredible. But how do we actually train these AI models? It sounds like a very complex process.
It is a complex process, but the core idea is actually pretty intuitive. Think of it like showing our detective a case file with all the evidence and the known outcome, guilty or not guilty.
Right, right.
So we feed the AI model a large data set of medical images, and these are paired with the known outcomes for those patients.
Okay, so it's all about pattern recognition. The AI learns to associate certain feature patterns with specific outcomes.
Exactly. The AI model sifts through those features that we've extracted from the images and learns to connect specific patterns with particular outcomes.
And once the model is trained, we can then apply it to new images and make predictions for new patients.
Precisely. So we present a new image to the trained model. It extracts the relevant features, and based on what it's learned, it makes a prediction about the likely outcome for that patient.
That's pretty amazing. But how can we be confident that the AI model's predictions are accurate? What if it gets things wrong?
That's a critical question, and that's where testing and validation comes in. Just like we wouldn't trust a detective with a low success rate, we need to make sure our AI models are reliable.
Okay, walk us through that process. What are the key steps involved in testing and validating an AI model?
So after we train the model, we put it to the test
Right.
on a separate set of images it hasn't seen before.
Gotcha.
So it's like giving our detective a brand new case and seeing if they can crack it using their training and experience.
So we're essentially evaluating its performance on unseen data to see how well it generalizes what it's learned.
Exactly. We then compare the AI model's predictions to the known outcomes for those test images, and then we calculate metrics like accuracy, sensitivity, and specificity.
Can you remind us what those metrics mean?
Certainly. Accuracy just gives us the overall percentage of correct predictions the model makes. Sensitivity measures how good the model is at correctly identifying positive cases. So in our example, does it correctly identify the malignant tumors? While specificity measures its ability to correctly identify negative cases.
Gotcha. So ideally, we'd want a model with high accuracy, sensitivity, and specificity, right?
That's the goal. But there's often a trade-off between sensitivity and specificity, and the prioritization might depend on the specific clinical application.
Okay, so we've validated our AI model.
Right.
But you mentioned something earlier about explainability.
Yeah.
What does that mean in the context of AI and medical diagnosis?
Explainability is actually one of the most crucial and complex aspects of using AI in healthcare.
Right.
Because we can't simply accept a prediction from, a black box algorithm. We need to understand why the AI model is making the decisions it's making. Think about it. Even if our detective solves the case, we still want to understand their reasoning, right? Their logic.
Absolutely. We need to be able to trust the process and understand the rationale behind those predictions so we can make, well-informed decisions, especially when it comes to something as important as healthcare.
Exactly. We're talking about people's lives and well-being here.
Right.
But achieving explainability with these complex AI models can be a real challenge. How do we make these intricate algorithms transparent?
Right, because it's not always easy to understand what's going on under the hood with these, advanced AI models. So how are researchers addressing this challenge of explainability?
Well, there are several approaches being developed. One strategy is to use simpler models that are inherently more transparent. So think of it like choosing a simpler case for our detective to solve, one where the logic and the clues are easier to follow.
So instead of using like a massive neural network with millions of connections, which can be like a black box,
Right.
we might use a simpler, like a decision tree model, where we can actually trace that decision-making process.
Precisely. Another approach is to use techniques like feature importance analysis. This tells us which features are the most influential in the model's predictions.
Oh,
So it's like identifying the key pieces of evidence that our detective relied on to solve the case.
that makes sense. And I remember from the readings that there are also techniques like saliency maps that can highlight the specific areas of an image that the AI model focuses on when making a prediction.
That's right. Saliency maps provide a visual representation of what the AI is seeing, so to speak. It
Yeah.
allows us to understand which aspects of the image are really driving its decision. It's a powerful tool for making AI more transparent and building trust in its predictions.
So it's like we can peek into the mind of the AI detective and actually see how it's analyzing the evidence.
Exactly.
All of this is fascinating, but I know the lecture notes mentioned a specific data set called adrenal MNIST 3D. Can you
Yeah.
tell us about that data set and how it relates to what we've been discussing?
Absolutely. That's a great example to illustrate how these concepts are applied in a real-world setting. So adrenal MNIST 3D is a data set of 3D images of adrenal glands.
Okay, what's so special about this data set?
Well, the adrenal MNIST 3D dataset focuses specifically on 3D images. This allows researchers to train and test AI models in a more realistic setting compared to just using 2D images. Remember, we talked about how those 3D shape features provide a richer understanding of an object's structure. So this dataset really allows researchers to leverage that richness.
So it's like giving our AI detective a more complete and detailed picture of the evidence.
Exactly. And by using this dataset, researchers can train AI models to distinguish between different types of adrenal gland tumors, which can be either benign or malignant, but based on their 3D shape characteristics. It's a very concrete example of how radiomics is being applied to address real-world clinical challenges.
All of this has been incredibly insightful. I think everyone here is starting to see how radiomics has the potential to truly revolutionize medical imaging and diagnosis. But I'm sensing that this is just the tip of the iceberg. There's so much more to explore in this, rapidly evolving field. What are some of the most exciting areas of research on the horizon?
Yeah, it does feel like we've only just scratched the surface here,
Yeah.
but I think we've all gained a much deeper understanding of how radiomics works and its incredible potential.
I agree. It's a field that's constantly pushing the boundaries.
Mm.
And as AI technology advances and we gather more data, the possibilities for improving diagnosis, treatment, and even personalized medicine are really exciting.
So where do you see this field heading in the future? What are some of the most promising avenues of research?
Well, one area that's generating a lot of buzz is the integration of radiomics with other types of data, like genomics and proteomics. So it's about combining the insights from medical images with, genetic and molecular information to develop even more precise and personalized treatment strategies.
Imagine having a complete picture of a patient's condition at both the anatomical and molecular level.
It's like piecing together a really complex puzzle using multiple sources of information
Right.
to get a clearer and more complete picture.
That's a great analogy. Another exciting area is the development of AI models that can not only detect the presence of disease, but also predict a patient's prognosis
Mhm.
and their likely response to different treatments.
So we could potentially use AI to tailor treatment plans for each individual patient, maximizing their chances of recovery and minimizing, potential side effects.
That's the vision we're working towards, and we're already seeing significant progress in this area.
All of this is truly remarkable. But as with any powerful technology, there are also potential challenges and ethical considerations we need to address as radiomics becomes more integrated into healthcare.
Of course.
What are some of those challenges?
Well, one key challenge is ensuring that these AI models are developed and used responsibly. We need to be mindful of potential biases
Right.
that might be embedded in the data that's used to train these models and make sure that they're not perpetuating existing healthcare disparities.
So it's not just about the technology itself. It's also about how we develop it and implement it in a way that's fair and equitable for all patients.
Precisely. Another crucial aspect is transparency and explainability, which we touched upon earlier. As these AI models become more complex, it's essential that we can understand how they arrive at their predictions. And this transparency is crucial for building trust among both healthcare professionals and patients.
It's about ensuring that we're not simply relying on a black box,
Yeah.
but rather on a system that we can, understand and trust.
Exactly. And of course, we can't overlook the importance of data privacy and security. We're dealing with highly sensitive medical information, and it's imperative that we have robust safeguards in place to protect that patient data.
Absolutely. So it seems that radiomics is not just a technological revolution, but also a journey that requires careful navigation of ethical considerations and a commitment to, responsible use.
You've hit the nail on the head. It's a powerful tool with immense potential, but it's our responsibility to use it wisely and ethically for the benefit of all.
Well, this deep dive has been an incredible learning experience. We've explored this fascinating world of radiomics, from its basic principles to its potential to transform healthcare. And it's clear that this is just the beginning of a very exciting journey.
Indeed, the future of radiomics is bright, and I'm incredibly enthusiastic about the possibilities that lie ahead.
I hope all of you are feeling inspired to learn more about this field. And remember, this deep dive is just a starting point. There's a vast amount of information available online and in research journals. So don't hesitate to explore further and delve deeper into the areas that pique your interest.
And as always, keep asking questions. The more we understand about this technology, the better equipped we'll be to harness its power for the greater good.
On that note, I'd like to leave you with a final thought to ponder. If AI can extract so much information from medical images, even revealing hidden patterns that we might miss, what does that tell us about the limits of human perception? Are we just scratching the surface of what's possible in terms of medical diagnosis and treatment? It's something to think about as you continue your journey in this fascinating field.
That's a great point to end on. It's a question that will continue to drive innovation and discovery in the field of radiomics for years to come.
That's all the time we have for today. Thank you all for joining us on this deep dive into the world of radiomics and AI. Keep exploring, keep learning, and keep pushing the boundaries of what's possible in healthcare.